Okay, so let's take on 3.2, Part A, in statistics. This is coming right off the backs of building scatter plots. So what we want to do today is now talk about, now that we built a scatter plot and we've described it, is how do we now make predictions? You know, what are the things that we're looking for? What is the big key points to this thing, right? So that's what we're going to be kind of focusing on today. So here we go. Here's a data set. I want to take this data set and I want to essentially build the data set, right? Now this is chirps per second, so this is crickets and temperature. So people say that the temperature and cricket chirps are very much related. So one thing I want to do is kind of figure out what is my explanatory and what is my response variable. Because is the chirping that is being done explaining or controlling the temperature, or is the temperature explaining how many chirps are done, right? So we use chirps to predict sometimes. So here's kind of what I would say. I'm going to go ahead and put my temperature. That's the least controlled variable on the bottom. I think that's going to explain how many chirps we hear per second from crickets, right? So that's what it is. And then so again, I could put all the, oh, I don't want that. I could put all of the temperature in on the X, and then we're going to put the chirps on the Y. But now I'm going to do this in my calculator, so why don't you do that with me? So here are the steps. I will run through them, so just kind of go along with me on this. So let's first go to our button on our calculators. Sorry, I'm looking for it. So I am going to go to stat edit. Okay, so hit your stat button. Let me see if I can write these for you. Let's go to stat button, then go to the edit button, and then we're going to go ahead and put in L1, L2. Now what you need to make sure, so I'm putting what you see in yellow in L1. I'm going to put what I see in green in L2. So this is all the data set. It's just been broken into two different sections. So L1 and L2. So you're kind of doing these backwards here, but so I'm going to go 88.6 in the first data point in L1, 71.6, 93.3, and so on. So you get the idea. I'm going to put all those in there. Okay, so now I put in the 15 points into the temperature L1. Okay, so I took a little pause, came back. So I'm going to do the same thing with L2. I'm going to put all the ones in green, but now I got to keep the exact same order. Do not mix up the order. So in these, I put 88.6 in the first one, so I need 20.0 in the first L2. 71.6 was in the second L1, so I need 16 in the second L2. So I'm going to start that. I'm going to go to the top L2, make sure it's cleared out. Then I'm going to go 20, enter, 16, enter, 19.8, and so on and so forth. And I'll be back to finish this off. Okay, and we just go all the way till I get 14.4 in the 15th spot. That is right across from the L1's 15th spot, which is 76.3. Perfect, L1, L2. Got it. Now we are good to go. Okay, so second edit, we put those things into L1, comma, L2, right? So we got those two things going. So what is next? What we want to do is hit our second button and then your Y equals button, which will get you actually to the stat plot function, okay? So second, Y equals, plot on. So then we want to turn on the plot, right? Make sure that you are hovering on the on, not the off. And then we want the first plot that comes up under type. It looks like this. Like that. We want to make sure that is highlighted. And then it says X list, L1, Y list, L2. That is the one. So I want to make sure L1, because that's where I put my X's. L2, that's where I put my Y's. And then mark it with whatever, and if yours comes with the color code, let it do the color code. So then we got that entered. So then, after we've done that, then we want to hit the zoom button, and we're going to go down to zoom stat. number 9, and then enter. Whoop, I'm getting error code. Sometimes you get an error code. What I want you to do is go hit your Y equals button and make sure there is no junk in there. Sometimes there's junk, and I don't know where it comes from, but it happens often that you get some random algebra functions in there or some random something in there. Go and try that, and if you cleared everything out of there, that looks good. I'm going to hit graph again, and I should get a graph. Now here's what we're looking at, temperatures. It looks like we got from 69.4, that's on the bottom half right there. And then the upper temperature, 93.3, that looks like the upper part, 93.3. Let's see what the chirps go from. 15, I see a 14.4. So we're going to go from about a 14.4 down here all the way up to 20. I see a 20. Okay, so that's all I'm doing, just kind of putting my range in there. And then, so what we're going to do is kind of just, I'm going to mimic what I see on my calculator screen. And this doesn't have to be perfect by any means, but we're going to want it to be close. Okay, that looks fine. I'm just going to readjust here. 93.3. Temperatures in Fahrenheit degrees, so people know. Okay, so that's what it looks like, right? So just a rough graph, and it's okay to just get rough graphs a lot of times in stats, even if we're doing this histogram stuff like this, right? So it looks like it might curve off a little bit at the top. Did I do that? No. Did I make it curve off? Anyway, so it kind of curves off a little bit at the top. Okay, so here we go. We have it plugged in there. I'm using our calculator function. Let's just think real quickly through FODs, form, outlier. So form, I'm going to give this as often as you can. If you can squeeze this into a linear form, that's what we want. So I'm going to call it linear, the positive direction. The strength, I'm going to call that probably moderate. It doesn't look like I can fit one straight line through there, so we're going to call it moderate. And outliers, I don't know if I really see any outliers. I think this kind of is moving in a general linear pattern, and they're all kind of bunched in there kind of nicely. Okay, so that's what we're doing kind of on the first section. So now let's get into some things let's do this thing called a regression line. So a regression line. So a regression line is any line that describes the general trend. And now we don't care about generic regression lines. We care about linear regression lines. That means a straight line, right? So a straight line that fits the pattern. So what we're going to do is, back in algebra, you probably used to do this like, hey, let's fit a line of best fit, right? Let's try to fit that right through the middle. All right, there we go, right? And we kind of did it with really no good statistical reason, but just like, hey, this looks like it fits it best. So that's kind of what this looks like when we're doing that. And that's great, but we want it a little more sophisticated than that. So here is what we're going to do in stats. We're going to let our calculator do it. We're going to let computers generate this most of the time. But we are going to be trying to fit our line y equals, remember we used to do mx plus b. In stats, we do it a plus bx. And we don't just do a little y, we do a little y hat. So let's talk about the different parts of this regression line, right? So anytime that you put the little hat above the y, we're talking about the predicted outcome. So the hat means predicted, right? So the hat, super duper important that you don't forget that little hat on top of there, okay? A is the y-intercept. Now you guys probably remember that from algebra. That is what we call the starting value, right? Is my y-intercept, or also known as the initial point, right? Something like that. Now the b value here is the slope. Or recall that slope is for every one value on the x-axis, it's the change in the outcome, right? Just talking about basic algebraic slope. For every one value on the x-axis, so for every one of these you add, this tells you how much movement you're going to get on the y, right? If it's negative, you're moving down. If it's positive, you're moving up, right? So that's what those would be right there. So we want to find this. We want to find this exact equation. So what we're going to try to do is dial these together, right? So that not only do I find the equation, but then I can write it right through there. So let's go back to our calculator. Let's hit our stat button. So I'm going to do this stat button on my calculator, and I'm going to go over to the calc button on my calculator, and I'm going to scroll down. There's actually two equations. Number 4 says lin-reg, linear regression, but number 8 also says lin-reg. I want to go to the number 8. Just check out the way that it says. It says a plus bx. That's the way we're writing it right now. So a plus bx. If you do that, hit enter. It says, where's your x list? L1. Where's your y list? L2. That's great. And we are going to hit calculate. When you do this, it calculates this for you. It does not put the little hat on it. You have to put the hat on it. So let's do it for this equation here. It is y hat, reading it right off the calculator. The a value should be negative 0.309. I'm going to do probably as small as these values are. I'm going to do it to 3 decimal places. Plus the b value is 0.212, and then x. Now let's get a little more AP-like on this. So AP is going to say you cannot just leave this general x and general y. So what is x and what is y? Y, remember, is the number of chirps. So check this. I'm going to just say the number of chirps predicted, right, the little hat, is equal to 0.309 plus 0.212. Instead of writing x, what is x? It is the temperature, right? So what I'm doing here is I am inside my equation. I am labeling as well. So there is the equation right there, and that is what is throwing a nice line of best fit. This is the line of best fit known as the regression line, but it's not just the regression line. It is known as the least squares regression line. Yes, least squares regression line. So what your calculator is doing is it is finding the least amount of squared area between your line and the points. So check this. This is what I'm talking about. This is pretty cool how you calculate because it does it super fast. But let's say this green line is my least squares regression line, or my line. So then what it does, it takes every point and it calculates the distance that it was from the point. And then it makes a squared area, right? And imagine it was shading an area. Then this one, how far is it from the line? Make a little squared area. How far is this one from the line? Even if it's above the line, it's going to create another square. It's going to do that. That one seems to be on the line. We'll call that one on the line. That one's a little bit off, so it will get a little squared area. This one's off. It'll get a squared area right here. This one is off. It gets a bigger squared area, right? It does that, and this finds a little square. You get the point, right? So, and this one, they all get this squared area. So what this line does, it rocks back and forth until it minimizes the squared area. So this does like thousands and thousands of iterations of finding, all right, put a new line in, now find all the new square area, put a new line in, find all the new square area, and so on and so forth. It does this thousands of times until it comes up with, hey, this one right here, chink, is the least squared area that we can possibly come up with. So we call it the least squares regression line. And again, it is called the least square regression line, better known as LSRL, right? So that is it right there. That is the line that goes through there. So once you found your least squares regression line, then you use it to make predictions, right? So now that we have this nice data set here, we can make predictions. And so you can make two types of predictions. You can make an interpolation, or you can make an extrapolation. So to interpolation means make a prediction within the current data. Extrapolation means make a prediction outside the current data. All right, so let's look at the current data, and we can determine which one, what this would be. So here is my data set. It goes from 69.4 degrees to 93 degrees, right? So these are degrees and temperature. So if I decided, I was like, okay, let's say it was, 80 degrees. 80 degrees. Guess what? 80 is inside the range of temperatures that we already have data for, so we're going to call this an interpolation. But somebody says, you know what? What if it's 100 degrees? And you want to make a prediction 100 degrees, that is called an extrapolation. Or somebody says, oh, hey, how about we predict, 50 degrees? That also is an extrapolation. Both of those in red are outside of my normal data set. So that is the difference between the two. Now, is there anything wrong with interpolating or extrapolating? No. But the further you get away from your data set on either side, the more caution you want to use with your extrapolated values, because the further you get, who knows? Like at 100 degrees, what if all our crickets died at 100 degrees, but it looks like they should have a ton of chirps, but they're dead, so they might not have any chirps. Or if you go too low, if you go to 50 degrees or 30 degrees, do crickets live then? Or do they even chirp? Who knows, right? So when you are extrapolating, you have to use caution. Interpolations are usually okay if it is a strong linear pattern with a really, really good R value, right? So then that will tell you how confident you should feel in your predictions. And then you're just doing a little algebra. So let's say I wanted to do an interpolation here. Interpolation of 80 degrees. So what we're going to do is we're going to have our number of chirps. And we're going to go negative 0.309 plus 0.212. And the temperature, did you say 80 degrees? I sure did. So there it is right there. So literally, I'm going to go in my calculator. Negative 0.309 plus 0.212 times 80. And I would get the predicted number of chirps to be 16.7. All right, 16.7 number of chirps. There we go. That's what it looks like right there, right? So these crickets, we would predict if it's 80 degrees out, 16.7. So again, extrapolation, could I do 100? Absolutely. Plug it in 100, but then always say use caution because we don't know what happens at 100 degrees. We don't know. We don't have any data on it. So we can make a calculation, but we don't want to assume that we know what that is. So that is using your least squares regression line. Here's another point, least squares regression line. Know that your least squares regression line will always go through the point average of the x values, average of the y values. So what that really is, that is like a hinge. This entire thing hinges at whatever, right? We find the x average and the y average, right? Whatever those are, literally average out the x values we have available to us and the y values we have available to us. And this is kind of the hinge. So then this line rocks back and forth on this until it finds the least squares regression line. So this value right here, the average of the x, the average of y, will always be in this equation, right? It'll always be, like if you put the average of x, you will get the average of y as the predicted value, right? Because your line always goes through it. The line is the predicted outcome. It is the line itself. It is what we are looking for there, right? So that is important. Again, how strong do we believe this equation? Well, if the r value is close to 1 or -1, the closer it is to the 1 and -1, the better we feel about this right now. Now, on the next one, we'll talk a little more about r squared and what that will get us, and some of the other different pieces that go into this. But for the most part, I want you to just be able to make predictions. First, create the least squares regression line and make predictions. We'll also do that in class using Stapplet.